Okay, for OST1, we are looking at reaction scheme question. So first question involving looking at A and then figure out what's the reagent conditions for step 1 and 2. So for such a question, the skills involved is to identify the functional group so that you can look at all the inter-functional group conversion. So for A, we have aldehyde functional group highlighted in yellow, alkane highlighted in orange. Okay, for B, alright, because you can see step 1 involved A to B, you have the alkene, and then you have the carboxylic acid. For C, what you have over here highlighted in blue is the primary alcohol. So clearly you can see it involves your aldehyde oxidizing to carboxylic acid for step 1, and your aldehyde reducing to alcohol. Similarly, your alkene reducing to alkene in step 2. Okay, so step 1 involving oxidation, step 2 involving reduction. So what are some of the oxidizing agents you can oxidize aldehyde to carboxylic acid? Okay, for example, will be your acidified dichromate with heat. Alright, of course, some of you may be wondering whether we can use KMnO4. Alright, in this case, KMnO4 will not be accepted. Why? Because your alkene, right, this alkene here, can also undergo oxidation that involve breaking of the CC double bond with KMnO4. So in this case, the alkene is intact, and as a result, alright, we want to preserve the alkene. We cannot use KMnO4. Okay. Okay, moving on, the reaction for step 2. In step 2, you can see that both the aldehyde and the alkane are simultaneously being reduced. So there's concurrent reduction of alkene and aldehyde. So think back in terms of reagent conditions. What can reduce both aldehydes and alkenes together simultaneously? It will be your hydrogen gas. Okay, whether you use platinum, palladium, or nickel. Alright, of course with nickel you need high temperature and pressure. Can reduce both your aldehyde and your alkene to the primary alcohol and its alkane. Okay, the only reducing agent you can't use in this case will be your lithium aluminum hydride or sodium boron hydride. Okay, so lithium aluminum hydride or sodium boron hydride cannot, because why? The alkenes, alright, will not be reduced. Okay, if not, then we'll move on to the next part where we are supposed to look at the structure of compound D and propose the reagents and conditions for step 3 and 4. So in this case, you'll notice that between this compound here and D, there's a gap. And then, but it forms, D can form this compound, and immediately you can see that involve a CH2 and H2. To count the number of carbons, you realize that this is newly added. So it's a step-up reaction. In this case, when you look at compound A, what are the functional groups that can exhibit step-up or that can participate in step-up reaction? Alright, step-up reaction. So step-up reaction, recall, involving a CN minus, alright, nitrile. So in this case, it's only your aldehyde functional group that can react with a CN minus. And in this case, we're doing a nucleophilic addition reaction. Alright, nucleophilic addition. What happens is that we are adding HCN across the CO double bond. So we can see we added a H and a CN across the CO double bond. Alright, so it's a nucleophilic addition. We added a nucleophile CN minus onto the carbon-carbon. So in this case, the CN is then reduced to CH2NH2, but importantly, you realize that the alkene is not reduced. So I need to choose a reducing agent that can reduce the nitrile group, the CN group, to CH2NH2 without reducing the alkene. So think back, what can reduce? So in this case, it's your lithium aluminum hydride, because lithium aluminum hydride, alright, cannot reduce alkene. Okay, so it only reduces your nitrile to CH2NH2. Okay, with that, we are done with question 1.